Okay, here we are starting our new unit, Unit 5, and here's our first lesson, Lesson 1. This unit is all about functions, so we're going to start with the concept of a function. So we've been studying numbers, and we seem to be able to do all the things we want to do with numbers, so why do we need to learn about functions? The answer is that if we expand our vision and try to find out about things that we ought to know, then we discover that numbers are not enough. We experienced some of this when we wrote linear equations to describe a situation. For example, average speed and constant rate allowed us to write two variable linear equations that could then be used to predict the distance an object would travel for any desired length of time. Functions also allow us to make predictions. In some cases, functions simply allow us to classify the data in our environment. For example, a function might state a person's age or gender. In these examples, a linear equation is unnecessary. In the last module, we focused on situations where the rate of change was always constant. That is, each situation could be expressed as a linear equation. However, there are many occasions for which the rate is not constant. Therefore, we must attend to each situation to determine whether or not the rate of change is constant and can be modeled with a linear equation. So let's take a look at example 1. Suppose a moving object travels 256 feet in 4 seconds. Assume that the object travels at a constant speed. That is, the motion of the object is linear with a constant rate of change. Write a linear equation in two variables to represent the situation and use it to make predictions about the distance traveled over various intervals of time. So we're going to let x represent the time it takes to travel y feet. So when we set this up, we would have 256 over 4, which is equal to y over x. Again, x being our independent variable and y being our dependent variable. If we've traveled 256 feet, then it has taken 4 seconds. So the way we would write this, if we write this in the term of y equals the rate times x, is by using the cross multiplication. So if we do this, 4 times y would give us 4y, 256x would give us 256x, and then in order to solve for the amount of feet being traveled, we would divide by 4, which gives us 256 divided by 4 times x. And when we simplify that, we end up with a constant rate of 64 as our unit rate. So any amount of feet is going to be equal to 64 times x. So what are some of the predictions that the equation allows us to make? Well, after 1 second, or when x equals 1, the distance traveled is 64 feet. Use your equation to complete the table in your lesson worksheet. So if we know that for 4 seconds, that is 256 feet, then we can also know what it is for 3 seconds, which would be 192 feet, for 2 seconds, which is 128 feet, and for 1 second, which would be 64 feet. So what is the average speed of the moving object from 0 to 3 seconds? Well, the average speed is 64 feet per second. We know that the object has a constant rate of change, therefore we expect the average speed to be the same over any time interval. So again, if this is 64 to 64 to 64, then we would have an average rate of 64. All right, let's take a look at example 2. We have already made predictions about the location of a moving object. Now, here is some more information. Let's say the object is a stone being dropped from a height of 256 feet. It takes exactly 4 seconds for the stone to hit the ground. How far does the stone drop in the first 3 seconds? What about the last 3 seconds? Can we assume constant speed in this situation? That is, can this situation be expressed using a linear equation? So how can we represent this situation? Well, you probably say that this is a situation that can be modeled with a linear equation, just like the moving object in example 1. So if this is a linear situation, then from the table we have developed in example 1, we already know that the stone will drop 192 feet in any 3-second interval. That is, the stone drops 192 feet in the first 3 seconds, or if we were counting the last 3 seconds, it would also be 192 feet. So let's take a look at what this looks like when you actually drop a stone from 256 feet. Alright, so you've seen a model of that. So if we were to slow the video down and record the distance the ball dropped for after each second, we would collect the following data. So if we were to slow this down and stop it, we could measure that from 0 to 1 second it dropped 16 feet, from 0 to 2 seconds it dropped 64 feet, from 0 to 3 seconds it dropped 144 feet, and from 0 to 4 seconds it fell and hit the ground at 256 feet. So we were saying that 3 seconds was 192 feet based on our example 1. However, if we look at 3 seconds, the ball actually dropped only 144 feet. So how is this so? According to the data, how many feet did the stone drop in 3 seconds? Which we just noted, it's dropped 144 feet. So how can that be? It must be that our initial assumption of constant rate is incorrect. So let's organize the information from the diagram in a table. So if we use the information from the diagram, we have 1 second is 16 feet, 2 seconds is 64 feet, 3 seconds is 144 feet, and 4 seconds is 256 feet. So what predictions can we make now? Well, after 1 second, or x equals 1, the stone drops 16 feet. And using the rest of the information, we can make only those 4 predictions. So let's make a prediction based on a value of x that is not listed in the table. How far did the stone drop in the first 3.5 seconds? What have we done in the past to figure something like this out? Well, we wrote a proportion using the known times and distances. So let's let x be the distance in feet the stone drops in 3.5 seconds. So using the information from the table, if 16 feet is 1 second and we have 3.5 seconds, then x would have to be 56 feet. If we use the second set of information, 64 feet in 2 seconds, but we're only looking for 3.5 seconds, then we would have 112 feet in 3.5 seconds. And if we use the last one, 144 feet in 3 seconds, but we want 3.5 seconds, then x would be 168 feet. So is it reasonable that the stone would drop 56 feet in 3 seconds? Well, no, that is not reasonable because our data shows that after 2 seconds the stone has already dropped 64 feet. Therefore, it is impossible that it could have only dropped 56 feet in 3.5 seconds. What about 112 feet in 3.5 seconds? How reasonable is that answer? Well, the answer of 112 feet in 3.5 seconds is not reasonable either. The data shows that the stone dropped 144 feet in 3 seconds. So what about 168 feet in 3.5 seconds? What do you think about that answer? Well, this answer is most likely because it is at least greater than the recorded 144 feet in 3 seconds. So we know that in 3.5 seconds it's got to be more than 144 feet. So what makes you think that the work done with the third proportion will give us a correct answer when the first two did not? Can we rely on this method for determining an answer? Well, this does not seem to be a reliable method. If we had only done one computation and not evaluated the reasonableness of our answer, we would have been wrong. So what this means is that the table we use does not tell the whole story about the falling stone. Suppose by repeating the experiment and gathering more data of the motion, we obtain the following table. So notice how it's done in half seconds. So after a half a second, we've traveled 4 feet. 1 second is 16 feet. 1.5 seconds is 36 feet. And so on and so forth until we get to 4 seconds. So choose a prediction you made before this table. Was it accurate? Why might one want to be able to predict? Why do we want to make predictions at all? Well, making predictions helps us make sense of the world around us. Some scientific discoveries begin with a prediction, then an experiment to prove or disprove the prediction, and then were followed by some conclusion. So now it is clear that none of our answers for the distance traveled in 3.5 seconds were correct. In fact, the stone dropped 196 feet in the first 3.5 seconds. Does the above table capture the motion of the stone completely? Well, no. There are intervals of time between those in the table. For example, the distance it drops in 1.6 seconds is not represented. So if we were to record the data for every 1/10 of a second that passed, would that be enough information to capture the motion of the stone? Hopefully you said no. There would still be intervals of time not represented. For example, what about at 1 and 61/100ths of a second? In fact, we would have to calculate to an infinite number of decimals to tell the whole story about the falling stone. To tell the whole story, we would need information about where the stone is after the first t seconds for every t satisfying the inequality t is greater than or equal to 0 and less than or equal to 4. So this kind of information is more than just a few numbers. It is about all of the distances in feet that the stone drops in t seconds from a height of 256 feet for all t satisfying t is greater than or equal to 0 and less than or equal to 4. So the inequality t is greater than or equal to 0 or less than or equal to 4 helps us tell the whole story about the falling stone. The infinite collection of distances associated with every t in the inequality is an example of a function. Only a function can tell the whole story, as you will soon learn. So let's take a look at exercises 1 through 6. Go ahead and try each one and check your answer after each one. So it asks us to name 2 predictions that you can make from this table. Well, they only provide 2 responses here, but basically you could pick any 2 from the table. Number 2, name a prediction that will require more information. Well, you could have picked any number that was not in the table between 0 and 4 seconds. In this sample response, they picked 3 3/4 seconds, but you could pick anything. So what is the average speed of the object between 0 and 3 seconds? How does this compare to the average speed calculated over the same interval in example 1? Remember that average speed is the distance traveled over a given time interval divided by the time interval. So if the average speed is 48 feet per second, then we would have 144 divided by 3, which is 48. This is different than the average speed calculated in example 1. In example 1, the average speed over an interval of 3 seconds was 64 feet per second. So that's quite a big difference. All right, looking at number 4, taking a closer look at the data for the falling stone by answering the questions below. How many feet did the stone drop between 0 and 1 second? You should have said 16. Between 1 and 2 seconds, your answer should have been 48. Between 2 and 3 seconds, it would be 80 feet. And between 3 and 4 seconds, it would be 112 feet. So comparing the distance of the stone dropped from one time interval to the next, what do you notice? Well, over each interval, the difference is a distance of 32 feet. So between 16 and 48 was 32. Between 48 and 80 is 32. And between 80 and 112 is 32. All right, for number 5, what is the average speed of the stone in each interval of a half second? For example, the average speed over the interval of 3.5 seconds to 4 seconds is, and again you are taking the difference, 256 minus 196 is 60, and the difference in time, 4 minus 3.5, is a half a second. So if you divide 60 by a half a second, you would get 120 feet per second. So repeating this for every half-second interval, for A you should have gotten 8 feet per second, for B 24 feet per second, for C 40 feet per second, and for D 56 feet per second. And for the rest of them, you have 72 feet per second, 88 feet per second, and 104 feet per second. Comparing the average speed between each time interval, what do you notice? Well, over each interval there's an increase in the average speed of 16 feet per second. So between 8 and 24 is 16, between 24 and 40 is 16, and between 40 and 56 is 16, and so on and so forth. Is there any pattern to the data of the falling stone? Record your thoughts. So if you have one time interval is 16, between the second time interval is 64, between the next time interval is 144, and for the last one is 256. So if you noticed any difference, you would have said each difference has a factor of 16. So we're multiplying by 16. 1 times 16, 4 times 16 is 64, 144 is 9 times 16, and so on and so forth. The pattern is actually y equals 16 times t squared, but you won't get to that until the next lesson. All right, let's wrap this up. So we know that we cannot always assume that a motion is a constant rate. We know that a function can be used to describe a motion over any time interval, even a very small time interval such as 1.0001 second. Functions are used to make predictions about real-life situations, such as motion, speed, and distance. For example, a function allows you to predict the distance any object has traveled for any given time interval. Constant rate cannot always be assumed. If not stated clearly, you can look at various intervals and inspect the average speed for those time intervals. When the average speed is the same over all of the time intervals, then you have a constant rate. When the average speed is different, you do not have a constant rate. And average speed is the distance traveled over a given time interval divided by that given time interval. All right, we'll see you in class.